Welcome back to part 2 of our lecture from chapter 3. In this part of the lecture, we'll be looking at the work energy theorem and the conservation of energy principle. Let's start with what is called the work energy theorem. The work energy theorem says that when we do work on an object or system, we increase the energy of the object. So for example, if I push on a chair, then the amount of work that I do goes to an increase in the chair's kinetic energy because now the chair is moving. In particular, if I do 100 joules of work on the chair, then the chair gets 100 joules of kinetic energy. Remember that one of the definitions of energy is the stuff that's transferred when work is done on an object or system. So in this case, all those joules of work that we do equal the joules of energy that the chair now gets. Our second example here, if we lift up a ball, the work done in lifting the ball increases the ball's potential energy because we're lifting it off the ground. So again, if we do 100 joules of work to lift up the ball, then the ball will increase its potential energy by 100 joules at the top. And we'll do some examples shortly where we actually put some numbers in. Another example is when we compress a spring. This time, the work that we do increases the potential energy of the spring, and this is what's called elastic potential energy. So again, if we do 100 joules of work on the spring, we have stored 100 joules of work in the spring as elastic potential energy. Another example, if we stretch a rubber band, the work done here also increases the elastic potential energy. This time, it's stored in the stretched rubber band. Our final example here, if we throw a ball up into the air, then the work that we do in throwing the ball up increases both the kinetic energy of the ball and the potential energy of the ball. And so in this case, if we do 100 joules of work here, it's going to be split between kinetic energy and potential energy. So the work energy theorem says or states that the work we do on an object by pushing, pulling, or lifting equals the total kinetic energy and potential energy given to the object. So the mathematical equation or formula for this work energy theorem is that the work done here is equal to the change in kinetic energy, that's delta KE, plus the change in potential energy, delta PE. Let's now look at an example of using the work energy theorem where we actually put some numbers in. So in this one, a woman lifts a 25 kilogram barbell from the floor over her head to a final height of 2.2 meters. The bar is at rest above her head. What is the average force during the lift? All right, so let's see if we can solve this problem using the work energy theorem. So the work energy theorem states that W, work, is equal to delta KE plus delta PE. Now, the change in kinetic energy is 0 because the bar started down on the floor at rest, and when it's all done, remember she's holding it above her head at rest. So the bar has 0 kinetic energy before and after, so this part is 0. What's changing is, of course, the potential energy of the bar because she's lifting it up, above her head. Now, we know that work is force times distance. So force times distance is equal to our change in potential energy. That's the final potential energy minus the initial potential energy. Since the bar started on the floor, the initial potential energy here is 0. So what we have is force times distance is equal to the final potential energy of the bar. Now, remember that potential energy for gravity is equal to mgh, where m is the mass of the bar and h is the height above the floor that the bar now is. So the distance that she is lifting it here, so remember this is force times distance is work, that distance is also the height. So you can see that the height here that she lifts it cancels the height here where the bar ends up. So those h's cancel out and we're left with just the force, average force on the bar is equal to the mass of the bar times g, and of course this is just the weight of the bar. Remember, we can calculate weight as mg. So no surprise here in this it's kind of a simple problem here. The force needed to lift the bar is just the weight of the bar. So we have 25 kilograms times g is 9.8, which is 245 newtons. Let's do another example using the work energy theorem. So Joe's 1,000 kilogram car has run out of gas. He gets out and starts pushing it with 500 newtons of force. How fast is the car moving after he pushes it 10 meters? And we will neglect friction in this problem. So here is our statement of the work energy theorem again. Work is equal to delta KE plus delta PE. Now, the car is on a level road here, and Joe is going to push it. But the car is not going to go up or down, so the change in potential energy of the car is zero. All right, so we can ignore this last term here, and now the problem just says work is equal to the change in kinetic energy. Well, again, work is force times distance, and the change in kinetic energy of the car is 1/2 mv squared. Remember, this is the formula to calculate the kinetic energy of the car. The car is starting at rest, so it has no kinetic energy. After he pushes it, it's going to have some speed, v for velocity, and this gives us the final kinetic energy of the car, which is equal to the change in kinetic energy of the car because it started with 0 joules. So in this formula here, all we have to do is solve for velocity because we're asked how fast is the car going after he pushes it 10 meters. So to do that, let's get rid of this 1/2 first. So I'm going to multiply both sides of our equation by 2. So the 2 shows up here. 2FD equals mv squared. Now I got to get rid of this m, so let's divide this side by m. And I'm going to reverse the order of the equation. I'm going to put the v squared over here is equal to 2FD divided by m. And finally, to solve for v, we have to get rid of that square, so we square root everything. So the velocity of the car is the square root of 2FD over m. The force was given as 500 newtons. The distance he pushes it was given as 10 meters. And the mass of the car, m, is 1,000 kilograms. So here is our final answer. 2 times 500 times 10 divided by 1,000 turns, and then remember it's square root of all that, and that turns out to be 3.2 meters per second. So this is a different way of solving this problem. We could have solved this problem using Newton's second law, F equals ma, and we could have determined what the acceleration of the car was, and then from the acceleration we could have used some kinematics equations to figure out the velocity. But that would have actually been more steps. The nice thing about working with energy and work here is that when we write the work energy theorem here and write it out in this form here, we see our answer. Remember, we're looking for velocity. There it is right there. We don't have to solve for acceleration first and then use some other formulas to figure out what the velocity is. Many times, in many cases, it's much more convenient and efficient to work with energy whenever we can. The solution to a problem is usually more direct. Let's modify that last problem we just did and make it a little more difficult and interesting. So this time, suppose Joe again has to push his 1,000 kilogram car, but now he's got to push it up his sloped driveway to get it into his garage up here. So the driveway is 20 meters long, that's this distance here, and it goes up a vertical distance of 2 meters, which is shown right here. He again pushes with 1,000 newtons of force the whole way up the driveway. How fast is the car going when it gets into his garage? Well, what's different about this problem is that the car is also going uphill. So the car is going to gain potential energy. So when we write the work energy theorem here, work is equal to delta KE plus delta PE. Now we have to include delta PE in our calculation because the car is changing its potential energy. So the work that Joe does here is doing two things. it's moving the car, which means the car gets kinetic energy, but he's also basically lifting the car, right? Using this ramp, he's lifting the car up 2 meters to get it into the garage. So that's an increase in potential energy. So once again, work is force times distance. The change in kinetic energy, same as last slide, 1/2 mv squared, but now we have to include mgh. That's the potential energy of the car when it gets into the garage. So again, though, the nice thing here is that we see the final answer is V, which is right here. So it's now, we're done with the physics. This is just an algebra problem, a math problem. We have to solve for V. So in order to do that, let's get rid of this term first, this mgh. I'm going to move it to the other side by subtracting mgh, and then we can multiply by 2 to get rid of the 1/2. Here's our 2 here. And we can divide by m to get rid of the m. So here's our m down here. And then finally, to get rid of the square, again, we take the square root of the whole thing. So now we can plug in our numbers. Remember, the force F was 1,000 newtons. The distance that he pushes the car in this problem is 20. All right, he's pushing it up the length of the driveway. So that's the 20 there. Here's the mass again, 1,000 kilograms. G is 9.8. The height that he lifts the car is 2 meters right here. And that shows up here. And then down on the bottom is M, the mass again, which is 1,000. So after carefully tapping this all out on our calculator and taking the square root of the result, we get 0.89 meters per second. We now turn to one of the most important principles in all of physics. This is the conservation of energy principle. Let's start by taking a look at a device called the pendulum. It's basically just a mass on a string that swings back and forth. But what we're going to focus on here is the energy of this pendulum as it goes back and forth. So when it starts over here at the top, it comes to a rest basically at each end. So we know that the kinetic energy is 0 then, since it's not moving. And since it's off the ground or the floor here, it has potential energy. So all of its energy here at the ends is potential energy. And then when it swings down to the bottom here, it's lost all of its height or elevation. So it doesn't have any more potential energy. But what it has here is kinetic energy, since it's moving. And what's interesting about the pendulum here is that as it swings back and forth, we can see that whatever potential energy it starts with over here, when it goes through and all that energy then becomes kinetic energy. And then over here, it's potential energy again. And by the time it gets back, it comes back to the same position. So meaning that the pendulum has not lost any energy. But what has happened is the energy of the pendulum has been transformed to different types. In other words, it's gone from potential energy to kinetic energy here, back to potential energy, kinetic energy, and then finally returns to potential energy. So this is an example of what is called the conservation of energy principle. It can be stated a couple different ways. The first way is that energy cannot be created or destroyed. It can only be converted from one form to another. Another way of saying this is that the total energy of an isolated system is constant. So remember this term conservation in physics means that the conservation of energy means that the amount of energy is conserved, which just means it doesn't change, it's constant. However, what we see in this demonstration here is that even though the amount of energy is the same, the type of energy is constantly changing. So energy can be converted from one form to another. It just can't be created or destroyed. So this conservation of energy principle is arguably one of the most important and fundamental laws in all of physics. There's a nice way to sort of visualize the conservation of energy, and that is thinking about buckets of energy. So this is a model to think about how energy is converted from one form to another without losing any energy. So let's assume that we start here with our pendulum over here, and we're going to hold this mass here and then release it so that it can swing back and forth. So when this pendulum first starts, it's not moving, it's at rest. But it has a height off of the ground here, so it has potential energy. So we can think of the potential energy bucket here as filled with energy, okay? And let's say, just to put some numbers here, let's say we start with 10 joules of energy in this pendulum. Our kinetic energy bucket here is empty. In other words, there's no energy in this compartment here. What happens as the pendulum starts to swing down is it starts to lose potential energy because it's dropping in height. However, it's speeding up because its velocity is increasing as it falls and swings. So what this means is we're taking some of this energy out of this bucket and we're pouring it into the kinetic energy bucket. So when it's halfway down, each bucket is half filled and there's 5 joules of energy in each bucket. As the pendulum keeps swinging to the bottom, we take this remaining 5 joules here in the potential energy bucket and we pour it into our kinetic energy container. So now at the bottom, what the energy model looks like is there is no potential energy left. All that energy has been transferred into the kinetic energy bucket here. And then as the pendulum starts to swing up, we start to take this energy here, remember there's 10 joules here now, and we start to pour it back into the potential energy bucket. So at some point here halfway up, we're at half and half. The buckets are each half full. And then finally, when the pendulum reaches its maximum height over here, it stops momentarily before it starts swinging back. And at that point, all of the kinetic energy has been poured out into the potential energy bucket, and we're back into, to this state that we started from. And then this, continues, it goes on and on. Now, one thing we could mention here is that, we said that energy is conserved for an isolated system. And what that means is that no energy is coming into or leaving our system. Now, if we did this experiment, in like a laboratory and watched a pendulum swing back and forth, we would find that it would swing, like this for a while, but after some time, the swinging amplitude here would become less and less. And so the pendulum would start to lose energy, basically, right? It's this arc here would become diminished and energy would be lost. Now, the question is, where is that energy going? And are we violating the conservation of energy principle? Well, the answer is no, we're not violating it, because what's happening here is there are some loss mechanisms, including friction, the string might be rubbing up here, and mostly wind resistance or drag. And what drag does is it transfers energy from the pendulum into the air around it. Because remember, drag is a bunch of, it's due to all the air molecules slamming in to our mass here as it plows through the air. So those air molecules now are receiving energy. It's like, this is like swinging a baseball bat and knocking all those air molecules around. So what's happening is the energy is being transferred from the pendulum into the room as thermal energy, okay? And so to make this, energy model more accurate, we could add a third bucket over here called thermal energy. And therefore, every time it swings, we would be transferring a little more energy into that thermal energy bucket. So if we consider the entire room or laboratory as our closed system, then energy still is conserved. Once the pendulum, loses all its energy, well, that energy is not destroyed, it's just transferred into thermal energy. So the conservation of mechanical energy can be stated as the initial total energy of a system is equal to the final total energy of the system. So remember, what conservation of energy means is that energy is conserved, which is just a fancy way of saying it can't be created or destroyed. It has to stay the same. Now, this is for a system, a closed system, where no energy is added to the system. So we can write the initial total energy here as E for energy, and down here our little name tag just says total energy, comma I for initial. Over here we have energy total, comma, F for final. And these two quantities have to be equal to each other because energy is conserved. It can't be created or destroyed. So total energy, you can think of that as total kinetic energy plus potential energy. And the I's here, again, remind us this is the initial kinetic energy and the initial potential energy. On the right side of the equation, we have the final kinetic energy and the final potential energy. So finally, let's write out, we know how to express kinetic energy. It's 1/2 mv squared. We know how to express gravitational potential energy. It's mgh. And again, these little I's here remind us that this is the initial velocity and the initial height. On the right side, we have the final velocity, 1/2 mv final squared plus mgh final. H final is the final height. Now, these terms, when we do problems, some of them may be set to 0. In other words, if the object is not initially moving, then this term here is 0 because VI would be 0, and we can just cancel it, cross it out. Likewise, if the object in the final state has no height, if it's sitting on the ground still, then H final would be 0, and this term can be ignored. So even though this equation looks kind of messy, and with 4 terms, we don't always use all 4 of these terms, and you'll see that when we work through some examples next. Let's get started with our first example. How fast is a 10-kilogram rock going when it drops 100 meters to the ground? Well, so this is one of those problems where we could solve it several different ways. We've seen how to do this with using kinematics, using dynamics. We even saw how to do it using the work energy theorem. So now we're going to solve it using the conservation of energy principle. And this is probably the simplest and most direct way to solve a problem like this. So let's think about the situation. We've got a rock that starts up here 100 meters above the ground, and we release it and it falls down to the ground. So let's think of this from an energy standpoint. What type of energy does the rock have up here at the top? Well, it only has potential energy because before we release it, there's no motion, right? So there's no kinetic energy. So the total energy up here is mgh, where h is the height of the rock. Now, the rock falls, and we know that potential energy gets converted into kinetic energy as it falls. By the time the rock gets down here, right before it hits the ground, it's lost all of this potential energy, and it has only kinetic energy, right? Because the rock has no height now, so h is 0. So the total energy of the rock is given by its kinetic energy, 1/2 mv squared. So conservation of energy principle says that the initial energy up here has to be equal to the final energy down here. So we just set these two things equal to each other. So in a sense, we could start this problem just like this. We could just say mgh equals 1/2 mv squared. And the nice thing about doing this is we see the answer we're looking for right here. Here is the final velocity of the rock. All right, we've already got the velocity right there, and now all we have to do is a little bit of algebra to figure it out. One thing you can do immediately is notice the masses, m's, cancel. So we can cancel those out, and we get this result here. We multiply by 2 to get rid of the 1/2, and we have solved for v squared. And then to solve for v, we just take the square root of our result. So we have the square root of 2gh. G is 9.8, and h is the height of the rock in meters, which was 100 meters. So this comes out to be 44.3 meters. So this is, again, using conservation of energy here, we can start this problem right here by just saying that the initial potential energy of the rock, mgh, is equal to the final kinetic energy of the rock, 1/2 mv squared. And, we see our answer as the velocity right there. So it's only a couple steps to solve this problem. For our second example, let's ask the question, how high does a 2-kilogram rock go if you throw it at 25 meters per second straight up? And then also, how fast is it going when it comes back down? All right, so the first thing to do here, again, is to make a little sketch here of what's going on. So now the rock is going to start down here. This is sort of just the opposite of the last problem we did. The rock starts at the bottom. So the initial energy of the rock is kinetic energy because the rock has no height yet, right? We're assuming that we're throwing it right from the ground. So the total energy of the rock initially is 1/2 mv squared. When the rock goes up and reaches its highest point, it stops and then of course starts to fall back down. So at its highest point, the rock has no kinetic energy because its velocity has reached 0. So it has only potential energy in the final picture up here. So the energy of the rock is mgh. So once again, we can equate these two terms here. The initial energy of the rock down here has to be equal to the final energy of the rock up here because of the conservation of energy principle. So again, we can just equate these two terms here, and this time we're going to solve for the height. So we have mgh equals 1/2 mv squared. We're going to solve for h. So again, the masses, notice they cancel out. We can divide by g to get rid of the g in front of the h. And here's our answer. The height is the velocity squared divided by 2g. So we can plug in our numbers. Velocity is 25. Remember to square that. And divided by 2 times 9.8, that'll give us a height of 32 meters. So again, this is a much more straightforward way of solving this type of problem than using the equations from projectile motion that we talked about earlier in the course in chapter 3. This is a real quick, it's just a couple steps here to find the height of this rock. Now, let's think about this problem a little further. How fast is the rock going when it comes back down and hits the ground? So the rock starts down here, we throw it up, it gets to this position here at 32 meters, and then it turns around and it falls back down. So we're trying to figure out how fast is it going when it reaches the ground again. Well, there's an easy way and a hard way to solve this problem. The hard way would be to go back to the previous example and redo that problem for an initial height of 32 meters. But we don't have to do that much. The simple way to solve this problem is to use conservation of energy. If this rock doesn't lose any energy, right, it goes up and it comes back down. If it has to have the same energy everywhere, then when it comes back down, it's got to be going just as fast as it went up initially. In other words, if we throw it up at 25 meters per second, when it comes back down, it's going to hit the ground at 25 meters per second. Why? Because the energy at the bottom is all kinetic energy, and the energy has to be the same, right? Energy is conserved. We're assuming no energy is lost here. We're ignoring wind resistance and drag and so forth. So by conservation of energy, it'll have the same speed when it hits the ground. Here's example number 3. You're riding home on your bicycle at 12 meters per second when all of a sudden your chain snaps, meaning you start coasting. Your house is at the top of a 10-meter hill. Can you coast to your house? Ignore wind resistance and friction. So here's the picture of what's going on. You're riding your bike along here on a flat ground here at 12 meters per second, and your chain breaks. So you can't pedal anymore, right? So all you can do is coast. So you're going to try to coast up this hill to your house, which is at an elevation of 10 meters above the ground where you started. So this is a good example of using conservation of energy principle to solve this problem. We know that the initial energy of the bike here is all kinetic energy, right? Because the bike is on the ground at an elevation of 0. There's no height, so there's no potential energy. So the energy of the bike is 1/2 mv squared. When the bike goes up the hill and gets to, let's say it gets to this point right here, well then you're going to slow down and come to a stop. So we're going to try to find out how high you can actually get. So at this point where your bike coasts to a stop, you don't have any kinetic energy anymore. Your energy is all gravitational potential energy. So the final energy, E final, is equal to mgh. Okay, so now this looks just like the previous problems where we have 1/2 mv squared equals mgh, and what we're going to solve for here is the height. How high up will the bike coast? So again, the masses cancel out, and we end up with this relationship here, and we can divide by g, so that h is equal to v squared divided by 2g, and this time the initial velocity was given as 12 meters per second. So we have 12 squared, which is 144, divided by 2, and g is 9.8, so that's 19.6 on the bottom. So the answer here is 7.3 meters. So what that means is at this speed, you only have enough speed to coast up to right about here at 7.3 meters above the ground. Notice the house, remember, is 10 meters above the ground, so therefore you did not make it to the house. You would have to be going faster to coast all the way up the hill. Our fourth example is a classic roller coaster problem. There are lots of roller coaster problems in physics, particularly when we're dealing with the conservation of energy principle. So in this one, we have a 500 kilogram roller coaster moving at 20 meters per second at the top of a 50-meter hill, and we will ignore friction and air resistance. So here is the situation here. The roller coaster up here, notice, is not at rest. It's moving at 20 meters per second. And it's also at the top of this hill, which has an elevation or a height of 50 meters. Now the roller coaster is going to go down this hill. So there's three parts to this. The first question is, how much energy does the roller coaster have at the top of the hill? So let's answer that one first. Well, we have to look at the roller coaster here and think about what types of energy does it have. So we ask ourselves, is it moving? And the answer is yes, of course. So it's got kinetic energy. The other question we ask is, does it have height? And the answer there is also yes. So it has potential energy. So the energy of the roller coaster is 1/2 mv squared, that's the kinetic energy, plus mgh, that's the gravitational potential energy. And we can fill in all the numbers. The mass of the roller coaster is 500, the velocity is 20, mass again here is 500 kilograms, g is 9.8, and the height is 50. So doing the math here, we end up with a total energy of 345,000 joules. Now part B says, how much energy does the roller coaster have at the bottom of the hill? So the roller coaster is going to accelerate down this hill and get to the bottom. The question is, how much energy does it have down here? Well, don't overthink this. We can use the conservation of energy principle and say that the energy at the bottom is equal to the energy at the top. So our answer, we already found that, it's 345,000 joules. The last part, how fast is the roller coaster going at the bottom after coasting down the hill? So obviously this roller coaster is going to pick up speed as it coasts down the hill. What it's doing is it's transferring its potential energy into more kinetic energy, okay? So we know what the energy at the bottom of the hill is, right? It was 345,000 joules. And the energy type at the bottom is all kinetic energy. There's no potential energy down at the bottom here because the height is 0. So our energy equation just says that the total energy of the roller coaster is equal to 1/2 mv squared, and all we have to do is solve for v. So we multiply everything by 2, divide by m, and then take the square root, okay, and we can fill in our numbers here. The energy at the bottom, remember, was 345,000, and the mass of the roller coaster was given as 500 kilograms, and then remember, this whole thing is square rooted. So this turns out to be 37.1 meters per second. And this answer makes sense. Remember, the roller coaster was going 20 meters per second up here. As it goes down the hill, it picks up speed because it's gaining kinetic energy. So it ends up going faster at 37.1 meters per second. Let's now take a look at an example that has elastic potential energy. So in this example, a spring-loaded toy dart gun has 5 joules of elastic potential energy stored in its spring when the gun is loaded. So the way these toy guns work is you push this plastic dart into the gun and it squeezes and compresses this spring. Now remember, when we squeeze or compress a spring, we are storing potential energy in that spring. It's called elastic potential energy, right? It's not gravitational potential energy like when you lift something up, but nonetheless, this is potential energy. So that energy is stored in the spring, and we're told there are 5 joules of energy now stored in that spring. Let's see, we're told the dart's mass is 10 grams. Okay, that's the red dart here. And the question is, how fast does the dart fly out of the gun? So when you pull the trigger here, it releases the spring, and all that energy in the spring gets transferred to the dart. So the initial energy, EI, which is 5 joules, right? This was the elastic potential energy, is equal to the final energy. Now, what is the final energy in the system? Well, it's kinetic energy. The dart is going to fly out of the gun, and it has kinetic energy. So the final energy is 1/2 mv squared. So notice we can now solve, we're asked to solve for the speed of the dart. That's v. So again, there's our answer right there. We just have to solve for it now. So let's get rid of the 1/2 first. Let's multiply both sides of our equation by 2. So we have mv squared equals 10 joules. And now let's divide by m, the mass of the dart. So I have 10 over m. And finally, to get rid of the square, I take the square root of the whole thing. So there's just a couple steps of algebra to solve for v. So v is the square root of 10 divided by the mass of the dart. Now the mass of the dart was given as 10 grams, but remember we have to convert that to kilograms. So since there are 1,000 grams in a kilogram, we have 0.01 kilograms for the mass. So on our calculator, we take 10 divided by 0.01 and take the square root of that answer, and we get 31.6 meters per second. So again, this problem illustrates the transfer of energy from one form to another. We started with elastic potential energy, and we ended up with kinetic energy of the dart moving, but those two quantities are the same. So hopefully at this point you have a pretty good understanding and feel of how to use conservation of energy. It's a different way of looking at a problem. You know, in the past we were kind of looking at the dynamics with forces, thinking about, you know, what's pushing and pulling, what are the net forces and all that. Now with our energy, we have a different way of looking at situations. We can just think in terms of energy, and that's often the easiest way to solve problems. So let's do a little conceptual quiz here. We've got 2 roller coasters here. They both are at the same height, and both roller coasters are starting at rest at the top. Roller coaster A, you can see, is really steep, and the roller coaster is going to glide down this really steep hill. Roller coaster B, with the same height, is less steep. It's a much longer hill, and it also has a loop here where you're going to loop upside down until you finally reach the bottom. So the first question is, which roller coaster will be going faster at the bottom? And the second question, which roller coaster will get to the bottom first? So go ahead and pause the video and think about this and see if you can answer these questions. And you know, be sure to use your knowledge of conservation of energy. Okay, well, to answer the first question, the answer is neither. It's a tie. And the reason for this is conservation of energy. Both roller coasters start with the same amount of energy at the top. They're both at rest, and they're both at the same height. When they get to the bottom, due to conservation of energy, they will both have the same energy at the bottom. So since all of the energy is kinetic energy at the bottom, that just depends on the speed of the roller coaster. So since the energies are the same, the speeds of the roller coaster are the same. So A and B are both going equally fast at the bottom. Now, which roller coaster will get to the bottom first? Well, in this case, A will get to the bottom first. A is going to accelerate faster. You know, it has a shorter distance to travel. B will take more time. It's going to go around this loop, right, which is going to take some time. And so by the time it gets to the bottom, even though it's going just as fast as A, it took longer for it to reach that final speed.